Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, and I'm actually doing a second video for this week on transformations. I'm not adding to the complexity of what we did last time. I'm going to stay exactly as basic as I did before. In fact, I'm going to do the same examples as I did before. But you know what I did last time was I did a lot of teasing about these things called rules, transformation rules, and I kept saying, you can do them with rules, you can do them with rules. But I said, oh, it's better to do it this other way. And look, I'm still agree, it's still better to do it the other way, meaning having the visual and such. However, that being said, number one, not all of us are visual learners. Number two, not everyone has the same access as I had when it came to things. I have something where I can literally rotate something, and if you're like my students in distance learning and you're looking at things on a screen, they're not expected to be rotating a computer all the way around, so having other options are always pretty decent, and transformation rules are not a bad one if you know how to use them. Now, before I begin, I need to throw out some caveats here. I need to make sure that you understand these. Okay, number one, you can't use these unless you know how to use them. And I know that kind of sounds weird, but you'll see what I mean when it comes to it. There are reasons why people might mess it up. Number two, you shouldn't use it unless you either have access to the rules or you know how to get the rules. I would not recommend that you memorize them. There are some of them that probably memorization kind of makes sense, like it's just a part of it. Like, for example, dilation, we kind of already do the rule in that way, reflection-ish sort of in translation. The ones that I'm really talking about are the rotation rules, can get kind of iffy, and reflecting across an axis, excuse me, an axis of symmetry that's not the X or Y axis. I wouldn't really go by a rule necessarily, but I'm going to show you how to do it with the rules, and I'm going to concoct them for you. So these screens are going to look very familiar to last time, in that we're going to look at the congruent transformations, the incongruent transformation, that is dilation, and 8 examples, 2 for each of them, translation, reflection, rotation, and dilation. Only some things will be written a little bit differently. I'm going to start by showing you how to get the rules, then we're going to use the rules for the examples. All right, enough of an intro. Let's go ahead and get started. And to do this, let's look at the congruent transformations again. By the way, when I keep saying this should be familiar, look at the video that was uploaded previous to this one. If you already saw that one, great. If you didn't see that video yet and you're watching this, I recommend you watch that video first to at least get an idea of what the heck I'm doing with these things, because these things I'm literally just going to follow the rules to make my make my transformations happen. I'm not going to explain, oh, and it's going to reflect across at least not too much. We will to start right here, but when I do the examples, rules only. All right, let's go ahead and get started here. Now, translation. Oh, so by the way, for all of these things right here, you can see there's this point, X, Y, this arbitrary start point. I'm putting it in the first quadrant. Even if it was in this quadrant right here, I could still call it X, Y. This X doesn't have to be negative. So keep a few things in mind here. This is very, very important, okay? Number one, X, and so what I kind of just stated, just because something says X doesn't mean that the number's positive. Okay, it could be negative. Number two, if you ever end up seeing a negative in front of an X like this, that means it's the opposite of the original sign. Okay, say X was -4 to start. Say that it was this point and it's -4, 2, like that. What's negative X? That's +4. If X is -4, the negative X is +4. So keep that in mind. If I ever put a negative X, that means, or a negative Y, that means it's changing the sign. It doesn't mean it's making it negative. It depends on what it originally was. And number three, this one is super crucial. X and Y are simply just numbers. And this is going to sound weird here because I'm going to be using, sometimes you're going to see something like this. Not exactly this, but sometimes you're going to see me switch the X and Y. This does not mean I go in the Y direction. The first number, the left number in a coordinate pair is the X direction. Y is just a number. If Y was 2 right here, that means it's a 2 now over here. Okay? I know this is already sounding kind of confusing. This is why I kind of heed the warning of using rules. X and Y are just numbers. If I switch them, if this number was 8, 2, now the number is 2, 8. Okay? That means I go 2 right and 8 up. This X doesn't mean the direction I go. X is a number. The number that's written on the right means I go up and down. The number that's written on the left means I go left and right. Okay? All right, those are the warnings there. We'll see how we do. This is why I don't always like doing rules, but I'm giving everyone an equal opportunity to try and do something with these that they might like. Okay, translation. Now, translation is the way that you move objects, left, right, up, or down. I'm only going to talk about in just a single point right here. Say that I wanted to translate an object A units to the right. That means that I take a point here and I move it 1, 2, 3, 4, 5, 6, A units over to the right there. Where is it now? Before it was at X comma Y. Now here, when I move this thing over right here, it hasn't changed its Y value, right? Its Y value still remains the same here, but the X value has now gotten a little larger. So Y is going to stay the same here, right? But this was X, and then I went A units over. I added A units to it. So now the new point here is whatever X was plus A. That's assuming I'm moving to the right. That kind of makes sense. But again, Y stayed the same. I didn't change it at all. Now what happens if I move it A units to the left? I move it 1, 2, 3, 4, 5, 6, A. Boom, A units over that way. Well, the same idea happens, but instead of moving to the right, I move to the left, and now that means I'm going to subtract A units that way. Y is still Y right here, but it's going to be X minus A in that case. You can kind of see if that makes a little bit of sense. Of course, we're going to be doing an example with that, but when you translate some units over, instead of counting how far over, you can actually do math for it as well. If I move 2 units to the right, I can add 2. Move 2 units to the left, I can subtract 2. Okay, let's check Y units. What if I move B units up and down? Now keep in mind what we just saw last time. Y stayed the same last time. This time if I just move up and down and keep X the same, X is going to stay exactly as is. So let's move B units up. 1, 2, 3, 4, 5, 6, B. That makes enough sense for me. So that point right there, if this was originally Y and I move an extra B units up, I'm adding B to that. So X stays the same and I'm adding B to Y. So X comma Y plus B. By the way, you can move A units and B units in a single thing. I'm just separating them to give you the illusion and the idea that, and you're going to see it on the next slide, 2 slides from now, but the illusion and the idea that, number 1, you don't have to, and number 2, just what's the directly up, down, left, right things. So let's go ahead and move it down now. So if I move it 1, 2, 3, 4, 5, 6 B units down, we're subtracting B from there, of course. And now we're looking at X comma Y minus B because we are subtracting there. So just keeping in mind, because normally they don't say translate -2 units to the right, because that would mean translating 2 units to the left. So if they say translate 2 units to the left, remember to subtract it. Or 8 units down, remember to subtract it. Okay, just keep that in mind. All right, there's translation rules. You're going to see more when we do the translation examples as far as what we do there. These are probably the easiest ones here. Reflection. I'm going to start by reflecting across axes. And axes aren't really all that bad because all you do, I want you to kind of take a look at this and see if it makes sense. Well, let's reflect across the x-axis. Oh, by the way, this notation, I'm sorry. This notation is saying, here's the original xy point that you take. And after you transform it, here's the pre-image point. After you transform it and make the image, here's where your image point appears, the corresponding point that you translated or reflected. Sorry about that. Yeah, these mean here's the original point that we're referring to. Here's where it looks after you transform it. Sorry about that. I forgot you haven't seen that notation yet. All right, let's reflect across the x-axis being right here. Now, naturally, if you see it as a visual, remember reflecting means going perpendicularly across, staying equidistant from that axis of symmetry, just like that. That makes enough sense. And I do want you to make sense of this, because I'm using it for rotations, where it's going to get a lot more complicated. But, you know, the x didn't change, right? Reflecting across the x-axis, the x didn't change. I'm still x units away from the origin over here. I've gone x units that way. So this x is still an x, right? Just stays as an x that way. See, before I went y units up, and this is equidistant y units down here. If this was y units up, that's a positive y. Not because it's up, just because that's what the y is. And this is the opposite effect, so this is negative y here. So what happens when you reflect across the x-axis is all that changes is the sign of the y value. It goes from positive to negative, or in some cases negative to positive, which of course you'll probably see in the examples. Now let's go ahead and reflect it across the y-axis, and I'm sure you can imagine what's going to happen next here. Instead, the y is going to stay the same, and the x is going to change sign. So if I drag this across and give a proper reflection like that, y has stayed the same right here, so I can write a positive y. But here's that positive x appearance, and now it's x units away in the negative, or on the opposite side. This is now a negative x in its place there. Pretty straightforward. I'm sure that if you made sense of that, It's probably one of the easier ones that, again, you can memorize. I don't want to use the word memorize because that's not really what the idea is there. There's a little more to it, but you just change signs of one of them. I'm sure the visual generally makes more sense. But of course, I'm going to be using the rules when we do this in the examples. Now, here's going to be a weird one. Reflect across x equals c and y equals d. What I mean is across any sort of vertical or horizontal line that's not necessarily your axis. X equals c could be this guy right here. It could be a vertical line, and remember, x equals c is a vertical line. Here's the c, whatever. Now, a couple things to this. All right. First of all, when we travel across, remember that if we're going perpendicularly, that means we're going horizontally. That means that your y value, your y value hasn't changed. So let's start there. The y value hasn't changed. That's why this part's written a lot smaller here. I'm just going to write y there. That's the easy part. Now, as we go across horizontally, we're going a certain amount right here. Okay. We're going a certain amount right here, and we want to traverse across equal amounts right there to get to the new spot. Okay. Whatever this new spot is. For now, I'm just going to call it x prime comma y. If you saw my previous video, you know what that's an apostrophe. It just means the transform part. This is my new point, x prime comma y. But I don't want to call it x prime. I want to use my numbers, like whatever c is, in my calculation to make sure I can get what it is. So here's the thing. As we traveled horizontally, this guy right here, this is a point on my line, but it also represents the midpoint between this point here and this point here. So I'll make it blue. Between this blue point here and this black point here. This is the midpoint of these 2 points in the x direction. It's the midpoint. And a midpoint between 2 points is calculated. You can calculate it by averaging your other 2 values. If I want to find out what c is as an x value, remember this is x equals c. I can average this x value and this x value here and divide it by 2. Add them up, divide by 2, that's taking an average. Now remember, we already know what c is in this particular example. When we reflect across x equals 7, we already know what that number is. What we don't know is what this number is right here. So let's get this one by itself algebraically. I'm going to multiply both sides by 2. Multiply both sides by 2 here, and of course that cancels out the 2 right there. And now you get 2c equals x plus x prime. And now I'm going to subtract x from both sides here. And so now you're going to get the x prime, that cancels here, x prime is equal to 2c minus x. So this is the guy that goes here, 2 times whatever your reflective line is right there, minus x. That's a handful, or a mouthful, whatever. That's something that even I personally don't memorize and know. I have to derive it and come up with it. If you practice it enough, I guess you know. And you know, this thing actually applies even to reflecting across the y-axis here. The y-axis is at x equals 0. See, in this case, c equals 0. 2 times 0 minus x is negative x. So see, that still applies, but generally so, for any other non-zero value, you have to do a little bit more to it. It's not just changing the sign. 2 times whatever number you have minus x. By the way, I remember that this is not on that next, the reflection slide when we do it, so I'm going to have to remember to rewrite these. I just didn't have enough room. We can do them as we go. 2c minus x, comma y. Now, if you can imagine what the next one is, to save some time, x is going to stay the same if I reflect across y equals d. That is, let me erase some of this at least just to give you the notion. Y equals d would be, say, a horizontal line like this, and this time x would stay the same. Right, now you reflect across this way, right, and the same idea is going to happen here instead, and I just chose a different letter here, and this will be 2d minus y. Same effect, same idea. Take a midpoint, isolate your prime transformed variable in the x or y direction, you get what it is. A little more difficult, a little more confusing there, but that's what it's going to be. We're going to use those rules if we have to reflect across any of those, which I think we have to do for one of the examples. Okay, that's the reflection one. And rotation is going to be kind of the weirdest duck. Actually, that one probably was the weirdest duck, but this one's going to have another little kind of nugget to it. Dilation is going to be super easy. In fact, what we did with dilation last time is kind of going to be the same thing in the last video. Okay, rotation. Now, one thing I did not mention in the last video with rotation is the 270-degree turns. So I want to make sure that I'm making sense of those. Let's talk about this kind of like a clock, okay? Or you turning, you know, in your seat or wherever you're standing. Okay, let's say I'm at 12 o'clock right here. Here's a cross on a clock. 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. If I want to go 90 degrees clockwise right there, 270 degrees counterclockwise is equivalent to it. In other words, you end up in the same spot. The reason is because 360 degrees is the entire rotation of a circle. 360 degrees is the entire rotation. So whatever you do on one end, subtract that from 360. 360 minus 90 is 270. You end up in the same place. Okay. 90 degrees clockwise is 270 degrees counterclockwise. That's why you see this part right here. They are equivalent. So if you ever see a problem where it says 270 degrees counterclockwise, just go 90 degrees clockwise. All right. Why go 3/4 of a circle? Why should I rotate my chair 3/4 of a circle that way when I could just go 90 degrees that way and be done? All right. Same thing with the other one. 90 degrees counterclockwise is 270 degrees clockwise, which of course you see right here. Okay. I just want to make sure I mentioned that first part. So, whoops, whoa, I don't want to drag everything there, and I don't want to hit that mic all over the place now. So let's go ahead and delete that, and let's talk about the actual rotations themselves. Okay, I am going to literally show you, or visually show you a rotation right here with this point. I'm going to take it and rotate it 90 degrees counterclockwise, and I'll show you where it ends up. And where it ends up, I want you to make sense of what I'm going to write for my rule. It's a little different. This is where I said the x's and y's are going to flip. Here we go. Let's rotate this point 90 degrees counterclockwise. Boom. Okay. Now, I'm going around the origin. All these ones are only around the origin. If I were going to talk about things not around the origin, which I didn't in the last video, the rules are going to get way hectic and way weird. Might as well stick to basic. Okay, now where did I end up? Here's something that I want you to keep in mind, and I want you to think about when we did the reflection example before. When you saw, hey, let's reflect across the x-axis. Doesn't it look like the x's are the same and the y's just, the opposite of? So keep that in mind. Those are just numbers. This was x comma y, this was x comma negative y, right? Because I went y down instead of y up. Okay, think about y in this last example, or in this example we're going to do here. Think about y as being going this far up, right? We go x units over this way, and y units up this way. That's why we get the point xy. And remember, we're rotating from the origin. Now we rotated this way right here. What does it kind of look like we did now? To me, it looks like instead of going x units right and y units up, it looks like I'm going x units upward now, right? I'm going x units upward, and I'm going y units to the left. And not only does it look like we're doing that, we are doing that. We're going x units upward and y units to the left. And remember, x is just a number. If x before was 6 units to the right, now we're going 6 units up. Instead of going 3 units up, now we're going 3 units left. So the rule going from the original point here, notice that the x that we went to the right is now the amount that we went up. So how do we write that? What we do is we write an x in the y coordinate portion. Remember, this x is not the direction that I go. This x is the distance that I go. Since I wrote it in the y coordinate, that's how much I go up or down. I'm going to go up or down this amount. That's where people can get confused. Next part, y as a positive number meant up, or if I was going in the x direction, it would mean going right. But understand, y is now going to the left. If y is going to the left instead of right here, if I want to write this in the x coordinate, I got to make sure that my y is going to be negative. This is a negative y, comma x. Whatever my numbers were before, I'm going to switch their spot in the coordinate pairs. I'm going to do this when I do the part in the video. Switch the spot in the coordinate pairs and switch the sign of the new x coordinate. New x coordinate. X coordinate. Not x value. X coordinate. All right? Switch its sign. Like I said, it can get confusing. This is why you don't want to, first of all, you don't want to memorize them. Second of all, it even is hard even if you know the rule. It can get hard even if you know the rule. Okay, so keep that in mind. All right, let's go ahead and go clockwise, 90 degrees clockwise instead. And I'm going to show you by doing it, instead of just going this way, I'm going to go 270 counterclockwise. 90, 180, 270. All right, we ended up in the same spot. All right, keeping in mind what we said before, and, the reason why I put this so extreme in one spot here is to say, hey, I'm kind of hugging this x-axis, kind of hugging the x-axis. So right here, I'm kind of hugging the negative y-axis in this point, and that kind of helps you say that this is that y distance right here. Remember, before we were going y units upward? Now it looks like I'm going y units to the right. Now, up and right are the same sign. They're different directions, but they both represent positive. So that means the sign for y didn't change here. I am going in a different direction. Now I'm going in the x direction, so I'm going to put y right here. But I'm still going the same sign. I didn't change sign this time like I did last time. X, however, x I was going to the right before, and now instead of going up x, I'm going down x. So x's sign is changing. It's becoming the y coordinate, but its sign changes. And these ones are going to be on the rotation slide, so I'll be able to put those in, boom, immediately. I'm going to go pretty quickly through the examples. Since I'm discovering them with you here and talking about them, I'm going to go through the examples to kind of make that a little more steadfast. All right. Those are the confusing ones. I don't know if I should have started with the confusing ones, but those are the confusing ones right there. Let's go ahead. Oh, I don't want to erase my point, of course. Let's just do some, not undo. Let's just kind of erase that and that. All right. Oh, don't want to erase that point either. All right, let's go ahead and do the 180 degree rotation. Yeah, keep them there. 180 degree rotation. This one's actually going to be an easy one. Check it out. 90, 180. By the way, notice that I did not mention clockwise or counterclockwise. 180 degrees clockwise is the same as 180 degrees counterclockwise. So what happens here? Well, instead of going, let's get rid of these. Instead of going x units right, I'm not going to draw that stuff, but instead of going x units right, it looks like I'm going x units left. Now x, the number, stays in the x coordinate, right? I was going x right, now I'm going x left. All that changes is my sign. X sign changes. Instead of going y units up, I'm now going y units down. In the y coordinate, just the y sign changes. This one's pretty straightforward. We go from xy to negative x, negative y, or opposite of x, opposite of y. Because remember, if they're already negative, all that happens is the signs change. And that's it. All that happens is the signs change. That's the easy one. That's another one to like memorize. I'm saying you can condition yourself to know by making sense visually what happens when you go from one point to the other. Remember, these are just single points. When I transform, I'm going to have to take 3 or 4 points to do within an object and then connect the dots. These are just single points to give you the rules, okay? And then we're going to use the rules. All right, one more sentence, dilation. This is going to be very fast here because this is kind of what we did last time already. I'm just going to kind of explain away the fraction part of it. All right, dilation means enlarging or reducing something to size, the object itself. And it's distancing itself from the center farther, or narrowing its distance, closer to the center, depending on whether you're enlarging or reducing. So right here, let's enlarge by a scale factor of n. N is some number. It could be 2, it could be 5, whatever. When you enlarge by a scale factor, what you do, and I'm going to say it point blank, is you multiply both of your coordinates. It gets twice as large, or n times as large, or whatever it is, but it also distances itself n times further away from the center. I'm doing it from the origin each time here, just like rotations. So I would multiply, so say that n was 2, just to kind of put where I'm going to put the points here. I'm going to make it twice as far away, n times farther away in x, and n times farther away in y. I basically doubled my distances here. So instead of being at xy, I multiply my x coordinate by n. Let me use the proper color here, though. I multiply my x coordinate by n, and I multiply my y coordinate by, by n. N times x, n times y. And that's all there is to it. That's it. Reduction by a scale factor of 1 over n. And this one's a little particular. I said 1 over n. What if it was 2 over n? It's going to be a different story. I'm going to talk about the 1 over n first, and then I'll give the little caveats in place. If you scale factor by 1 over n, it becomes a reduction. That means you're getting closer, assuming n is an integer. Because if I do 1 over 1/4, that's actually 4 times larger. But if n was, say, 4, right, I'd take it and I'd get it 4 times closer to the center, something like that. It becomes 1/4 the distance that it originally was in both x and y. If it's 1 over n, I take my x coordinate and divide it by n, and my y coordinate and divide it by n. Now that one I was getting a little too particular with, meaning that's only if it was 1 over n. I mean, what if my scale factor was 2/3? Now what do I do? Because now there's a 2 on top. It's not a 1 anymore. Well, at this point, you got to really just multiply by 2/3. If you don't know how to multiply by a fraction, your value really multiplies with the top number. It's really 2 times x divided by 3 and 2 times y divided by 3. Multiply by 2, then divide it by 3. But those are your rules there. I'm really going to be sticking to just talking about this one. Whatever your scale factor is, I'm just going to multiply by it. And if it's a 1/2, I multiply by 1/2. That's the same as dividing by 2. Okay. All right, let's go straight to the examples here. Now I've spent 25 minutes doing a lot of babbling. This is really what you want to see, but that's how you got to learn it. That's discovery. You've seen the rules. Now let's jump into it here. These examples are the same as last time. Now you're just going to see them in a mathy way, what I'm going to do with it in a mathy way, and then we'll plot the points from there. Okay, so translation here, we're going to go by this rule. A and B are real numbers that you can use to add. Remember, we can subtract as well if A was negative. It depends on what I'm doing. Like 9 units to the left, that means that my lowercase a value kind of is a -9. Left means negative there, right? So translate the quadrilateral 9 units to the left. Notice that it doesn't say up or down. That means that my B value, I'm adding nothing. B is straight up 0 right here. And I'll literally add 0 to begin with, and then I'll just plot the points based on that. All right, it helps to write out what the points are for yourself, so when you're actually calculating it, you know what you're going to do. If my original A point is at 2, -5 right here, my new transformed point A prime, I'm going to take my 2 for x, and I'm going to add -9. I'm going to subtract 9. And I'm going to take my -5, and I'm going to, of course, add 0. There's nothing to that. It just becomes that. So 2 minus 9 is -7, and -5 plus 0 is -5. That becomes -7, -5. My new A prime value is right here. There's A prime. Right, that's how you do this. I'm not going to add 0 literally each time. I think you know what I'm doing here now. 8. We're going to do 8 minus 9, and this number is going to stay as a -2. In fact, I'm going to write these ones all out straight up now that you know, so I don't keep switching tools. 7 minus 9, and then -9, and 3 minus 9, and -8. So let's go ahead and figure out what those ones are now. 8 minus 9 is -1. 7 minus 9 is -2. 3 minus 9 is -6. So that's where I'm going to plot these last points here after calculating, and of course that's where they end up. So -7, -5, -1, -2 is my B prime, and then -2, -9 is my C prime, and then my D prime is going to be at -6, -8, I believe is right there. And then of course I should connect my dots, and then I'll be set. So that's another way of translating. Of course, counting is equivalent. You know when a good time is to use a rule, specifically for something like translation, is if your numbers are huge. What if you have to translate, from A being 100, comma something to -768, comma something, right? It's better to just do the subtraction now instead of count, 700 times. So, sometimes it's just more worth it based on what you're doing. But there's the translation. It should equate to the last one I did. And here this time, let's do a little more mental math, if that's cool. I'm going to do these numbers. It says 5 units right and 7 units down. So here I'm going to do +5 minus 7. I'll just put them right here. +5 minus 7, +5 minus 7, +5 minus 7. That sounds good. -5 plus 5 is 0. 6 minus 7 is -1. I'll plot them afterward. -1 plus 5 is 4. 6 minus 7 is -1. -2 plus 5 is 3. 2 minus 7 is -5. So now let's plot those points there. T prime, 0, -1. It's good to label your points right after so you know what corresponds. 4, -1 for U prime. And V prime is at 3, -5. So not too harmful. This was a relatively harmless tactic in doing this. I kind of do that already sometimes. You might see me say, oh, let's go 9 left. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9. And what I'm doing is I'm doing 8 minus 9 in my head already. I know this is at 8, and I know it's going to end up at -1. This is just writing the rule. This is showing how you use the rules literally, and you can write them down and compute. And that's what that is. All right, that's translation. Let's move on to reflection here. Reflection is, and I have the ones for the X and Y axes right here as you reflect across. I'll be sure to write down the one when we have to reflect across this line in a bit. Excuse me. So reflecting across the x-axis right now, we're going to take our points and we are going to switch the sign of the y value in all of them. This is going to be a very fast right here. The x value stays the same. 2873, 2873. These do not change. X values stay the same. Y values change sign only. -5 becomes a +5, -2 becomes a +2, and so on and so forth. We can plot the points and we'll be done. This is a case where it's actually pretty good to do this. By the way, in the other video that I did, of course, I only had the graphs. I didn't give you coordinate pairs. Not every transformation problem that you're given always gives you a graph. Sometimes they just give you the coordinate pairs, no graph at all. So the rules sometimes make a little more sense. Of course, I'm one of those when in doubt, draw it out kinds of guys. So I'd probably draw it anyway to make sense of it, unless I really know what I'm doing, like this reflection one. I personally understand what I'm reflecting across when it comes to this. Those are different color greens. Those are different color greens. And there's our reflection. You want to double check your work and make sure it makes sense. I can see the reflection I'm doing there. I think that tends to hold water. I think that one works out. All right, reflecting across the line x equals 2. This was the vertical line. Okay, this was the vertical line here. I'm just going to draw it really quickly so you can see once again what that means. The reflection's going to go over here. That means the y values are going to stay the same. The y values are going to stay the same. So you remember which one this is when we reflect across that line there? Because I'm going to get rid of that. I just did. It's now going to say, instead of that, we're going to change our xy's to, remember, it was 2c minus x comma y. The y is going to stay the same. Let's write that out first. 6, 6, 2, clip, clip, boom. And let's do these ones here, -5, -1, -2. This is my c value. C equals 2. So we're going to use this formula here. We're going to do 2 times 2 and then minus whatever x value we have. Now notice these x values are negative. That means you got to subtract a negative, which becomes addition. So I'm going to save time for writing. I'm just going to put a plus automatically. If you ask, hey, why do you put a plus? Because I'm subtracting a negative. So 2c minus x for each point. T prime, 2 times 2 minus -5. U prime, 2 times 2 minus -1, which is plus 1. And then this v prime, 2 times 2 minus -2. All right, 4 plus 5, 4 plus 1, 4 plus 2. That's what we're doing here to get those values. We'll see if it looks like it makes sense. 4 plus 5, 4 plus 1, 4 plus 2. 4 plus 5, 4 plus 1, 4 plus 2. Okay, 9 comma 6. Let's see how t prime looks after this with all the other ones. Here's my t prime. Now remember, it's not reflected across the y-axis. It's this line invisible right here. I'm going to put it up later and we'll see if it looks like it's good. 5 comma 6 for u prime. And v prime 6 comma 2. This is a reflection here. Let's see how this one ends up looking. Is she a looker? Does it look like a reflection? Well, it looks like the object reflected, but did it reflect across the correct line here? So let's see. Yeah, it looks like they're equidistant right there. 3 units apart, 3 units apart, 4, 4, and whatever. Right, so there's the reflection there. So I use the rule. The rule helps, but I'm not going to memorize that tomorrow. Right? I don't remember which one it is. You know, I personally, when I talked to you about this, when I said we're going to reflect across this line, I needed the visual to remember, even if you do it mentally, to remember and make sense that my y's were going to stay the same and my x was going to change. I just had to remember what the x thing was to put that in. All right, so there's the reflection. Let's go on to rotation. So rotation, I do have the rules here for you. Let's see if this makes sense. I think once you pick it up after the first one, I think you'll be fine with it. It's just knowing the rule and making sure you know how to use it is the important bit here. And remembering that an opposite of a number means it changes its sign. Doesn't mean it makes it negative if it was already negative. Remember that. All right, let's rotate it 90 degrees around the origin. Remember, as last time here in the last video, if they don't tell you, the default is actually counterclockwise, not clockwise. So that's what we're going to do, counterclockwise around the origin. So we're going to do this one right here. Notice I didn't put 270 anywhere. This, if this said 270 clockwise, just 90 counterclockwise is what this is. So we're going to use this rule here. We go from xy to -yx. Now what this means again is x is a number. X are these numbers here, 2873. What I'm going to do is I'm going to put the numbers 2873 into the y coordinate from the transformation. A was 2 comma something. Now it's going to be something comma 2. Okay, that's what's happening. That's what's happening here. The x value is becoming the y coordinate. And then 8 goes in the y coordinate for b prime. 7 is the y coordinate for c prime. And 3 is the y coordinate for d prime. The y coordinates go over to the x. So, excuse me, the y value goes over to the x coordinate. With one caveat, the sign changes. All these negative signs are going to become positive. And think about it. This is a 90-degree counterclockwise rotation. If I rotate this thing 90 degrees, where do I end up? First quadrant. And this is a really good check to say for yourself. Before you even do these, say to yourself, if I rotate this 90 degrees counterclockwise, the points are going to end up in the first quadrant. That means all the signs should be positive. That makes sense. So that's what's going to happen here. Negative 5? Nope, positive 5. Change the sign from this to opposite. Negative 2, positive 2. Negative 9, positive 9. Negative 8, positive 8. So that's what these become here. I'm going to plot the points. Hopefully that made sense, right? Developing the rule wasn't so fun and easy. I acknowledge that. I understand that. That was a little tougher. But now after you see this, that's what we do with them. Remember, I'm not going Y units down or anything like that. No, I'm just changing the sign and I'm going that direction left to right. So 5, 2, 2, 8 for this B prime. C prime is 9, 7. I think that's it. Don't want to write it 7. That's C prime. And D prime is 8. 8, 3. D primes. Connect the dots and we'll be set. And there's my rotation. So hopefully that made sense. And arguably that was the harder of the two problems here. The next one's going to be 180-degree rotation. And if you saw the early part of the video, then you know that all we got to do is swap some signs around and we'll be set. But that is a rotation. Notice where B started. Rotation right there. You probably saw the earlier video, so you know. There's the rotation. There's the rule. That's how I used it. All right. That's why we go to school. All right. Rotate triangle TUV 180 degrees around the origin. Again, clockwise, counterclockwise, doesn't matter. Here, we take the X and make it the opposite sign. We take the Y and make it the opposite sign. So they're going to stay in the same spot, but the signs change. Instead of negative 5, 6, I'm going to get 5, negative 6. Pretty straightforward. These are the easy ones. Negative 1, 6, 1, negative 6, and negative 2, 2, 2, negative 2. And that's it. Just got to plot them now. 5, negative 6. That's T prime. Let's see if it was over there. It's upside down now. It's right there. 1, negative 6 right here for U prime. And then V prime 2, negative 2. So again, hopefully it's making a little bit of sense. I'm going to totally acknowledge that those who didn't understand rotation in the first video probably like this one more and go, yeah, why didn't you give me rules earlier? I really want you to understand the rules, right? You won't always have access to them. So you either got to know how to come up with them on your own or make sure you have that access. The visual thing is equally as important, and sometimes if you have patty paper or physical sheet of paper, you can rotate it. I would prefer doing that anyway. I don't like going to the rules unless it wasn't drawn and they don't want me to draw it. That would be a different story. Okay, last two examples are through dilation. Now, I'll be honest, we did dilation last time the same way, only this time we're going to write down the numbers. This should go pretty fast. I'll probably end at the 40-minute mark. That's what I'm hoping for, just above 37. All right, scale factor of 2 centered at the origin. We're going to dilate. What we're going to do, the scale factor is n, any non-zero number. Right? If we dilate, the scale factor is 0, the numbers disappear. By the way, these numbers can be negative. I'm not going to get into that, but they can be negative and they kind of becomes like a rotation. 180-degree rotation, but a dilation. So n is the number. We multiply by our values here. 2 is going to multiply by negative 5. You okay with that? 2 times negative 5. 2 is going to multiply with positive 5 here. So that's negative 10 and positive 10. So it dilated by growing twice as large in both x and y coordinates. That's t prime. U prime was negative 1, 5. Let's do times 2 times 2. That's negative 2, comma, positive 10. So negative 2, comma, positive 10, right? Not only do they separate themselves twice as far from the origin, but of course the object gets twice as large. Negative 2 times 2 and 1 times 2 is negative 4, comma, 2. So negative 4, comma, 2 right there. And again, you can probably just do this mentally. I'm just giving you the visual thing to tie in with all the other ones. I forgot to change the colors along the way, but that's okay. So there's that one there. There's the dilation. Remember, it's centered from the origin, right? This is your center of dilation. Everything's growing from there. Everything's growing from there. And it kind of casts a shadow out like that. It's kind of neat. I like it. All right, last one here. This is a scale factor of 1/3. Remember what happens to scale factor of 1/3? I am going to be doing these numbers times 1/3. But what is 9 times 1/3? What do we do there? That's the same thing as dividing them by 3. Okay, all these numbers are going to divide by 3. So I'm just going to kind of write them right here, just to kind of have fun with you here. Divided by 3, divided by 3, divided by 3, divided by 3, divided by 3. Thankfully, all these numbers are divisible by 3. That's not always the case. Kind of got to rough it out sometimes. 0 divided by 3 is 0. Negative 6 divided by 3 is negative 2. This is 3 and negative 1. This is 2 and negative 3. And this is 1 and negative 3. All right. 50 seconds left. Can we finish in time? 0, negative 2, A prime. 3, negative 1, B prime. Here we go. 2, negative. I'm going to have a wrap-up beat with this, so I probably won't finish right at 40 minutes. I don't even remember how long the other video was. If it was longer or shorter, I have no idea. All right, just connect the dots kind of fast there, and there's the reduction there of scale factor 1/3. It's 3 times as small, 3 times closer to the center of dilation, which was the origin. All right, so that is it. You have now learned how to, if you saw both videos, you've learned how to do transformations through its visual appearance and what the transformations mean and how you apply them by counting and doing the skew and rotating and flipping, all that stuff. And now you've seen them through calculations and the rules. The rules get kind of iffy. Make sure you pause the screen at any rule to see what it is. I wrote them at the very beginning. Hopefully that helps. That'll do it for this one, guys. This is Mr. Robinson. I ended at 40 minutes. Take care.